Thank you very much. Thank you, Simone, Tim, and Courtney for inviting me. It's really been like a couple of years ago, and I've been really looking forward to this. I thought this day would never come, but here it is. Thank you all for coming, in the late afternoon. One correction to all this, wonderful things you said about me. I do not have a master's degree from Moscow University. Now, this is a very correct, not natural mistake. If you read my bio, it says that I've attended a master program. So in Moscow, we had to stay 5 years to receive the master's degree. We did not have a bachelor degree. I left after 4 years to move to Columbia PhD program. So I am a college dropout. I do not have a bachelor degree. So like proud, Most people become CEOs and make a lot of money after they do. Exactly. I do not hold a master's degree. Exactly.
Can you speak Russian, Katya?
Да.
Да? Oh, we can try a little, if you like.
Sorry?
We can try a little if you like. Можем попробовать.
Да, мы можем, да. Okay. Anyway, okay. Thank you so much. So, let us begin. First of all, obviously, I do really welcome questions. It's a big audience, and sometimes it's maybe not so easy to speak up in a big audience, but I'll try to ask you something, so maybe it will give everybody courage to speak up, raise your hand, discuss, because that's one of the best things we can do, I think, especially in late afternoon, long lecture after some other long lectures. Okay, so what is derivative-free optimization? So we need to start with that, right? So I'm going to give you definition by example, right? This is one of the best mathematics tricks you can do. But definition by example is almost as good as proof by intimidation. I will maybe try to do that later. I'm going to do a few examples, just so that you keep that in mind, because tomorrow I'm going to talk about derivative-free optimization again, and it's really important to keep in mind where the applications are coming from. So, first example. Let's say you have two three-dimensional objects. So I can hear myself from somewhere here. I don't know, maybe. Yeah, let's try to get rid of it. You did this before, right?
Yeah, on Zoom.
Yeah. Right, I thought it would stay mute. Okay, good. Thank you. It's super annoying otherwise. Oops. Yeah. Okay. So we have two three-dimensional objects. I cannot do three-dimensional objects in 2D, but you can imagine. So my purpose is to take one of them and superimpose it with the other, so that I maximize the volume of the intersection, right? So I have essentially what my, parameters are. I have to move this object, the center of this object, by some vector. So that gives me 3 different variables. And then I can rotate this object. So that's another 3 different variables for the vector around which I'm rotating. And then the angle of rotation is another one. So 7 decision parameters, which will define how I superimpose these objects on each other. And again, the purpose is to maximize the volume of intersection. This application actually, something that a colleague of mine was working on, and I worked with him on this specific application. He was from computer science, and the application was to detect properties of proteins by basically having the folded objects, protein objects, superimposed like this, maximizing volume of intersection, and that somehow could tell the specificity of 2 protein, that is for example, how they react on different interact with different drugs, for example, how that correlates. Anyway, so he had an algorithm that would compute the volume of intersection once the superposition is done. So he had a way to compute the volume given you know, given the rotation and translation of one of the objects. So how he computed these volumes, I don't know exactly, but all I know is that there was involved the some kind of a grid. So you construct a three-dimensional grid, and then you basically compute, you know, the number of cubes that fall, and half cubes or whatever that fall into the intersection, right? So here you now already see. So this function, which is the volume of intersection, right, is a function. And if the bodies are kind of nice and smooth, this function would also kind of be nice and smooth. You can rotate the one body a little bit, and the function will change a little bit. But the way it is computed by discretizing the space. And the rougher the discretization, the sort of the more error there is in computing that volume, right? Anybody have any questions about this? So we are computing something which is computed by a computer program. It's a function that we want to optimize. It's computed by a computer program, and it is computed inexactly. And moreover, we have a way to computing it more or less accurately at cost, right? Clearly, if you discretize more finely, you can approximate volume better, and the algorithm would run longer. Okay, so this is a very normal example for us, and everything here is deterministic. Okay. So another example, so this is example number one. Example number two is queuing. So let's say I have some kind of a queuing system with servers, and customers are coming in, and I have maybe a way to route them to servers. And there are various ways I can ask this question. So I can ask, what's the best policy of assigning the next customer to a server? And I can parameterize my decision with some continuous parameters, or I can decide on what kind of servers to hire. And the servers come at, for example, different service rates. Some are faster than others, but they're more expensive. And overall, I want to optimize the average waiting time of a customer in the queue, for example. Right? So now, this is a stochastic system. There's nothing deterministic about it. Now, I have, how can I compute the average time of customers in a queue? I will simulate the process, right? So the usual way of simulating a queue, you have some kind of Poisson process of arrivals. You have service times. They're possibly random. They could be deterministic. You simulate the service process, and then you basically run it for multiple time periods, and then at some point you stop and you average the waiting time per customer, for example. So this is a queuing. So queue, and this is stochastic, and this is inexact deterministic. Okay, and this is stochastic. Okay. So again, I have an objective function which I can compute as a simulation process that is a computer code that I can run it once and get one estimate of the expected waiting time, or I can run it 100 times and get 100 estimates of expected waiting time and average them out. And I can run it 1,000,000 times and average it out. Right? So basically, I will never get the exact expected waiting time, but I can compute it more and more accurately depending on how much effort I put in. Okay, great. Example number three, binary classification. So hopefully everybody's familiar with binary classification. We have, I don't know, two sets of points, a positive and a negative one. And I want to, so nobody thinks of binary classification as derivative free, but you'll see in a second why. So I'm constructing a binary classifier defined, defined by parameters, right? So this line here is defined by its, you know, the parameters, like say the orthogonal vector, right, that defines this line. Okay, and anytime I have a particular classifier, I can compute expected error. not expected loss, but expected error, 0, 1 loss. So the probability of making a mistake, right? This is what we ultimately want to optimize. If my distributions are nice and continuous, you can imagine that small perturbations to this separating line, right, will result in small perturbation in probability of making an error. So my function as a probability of making an error would look something possibly like this. It may not be convex, but it's probably nice and smooth. And you can show that in certain distributions it's nice and smooth. However, we always use discrete data sets, right? The data sets that we actually have our, for training is discrete. So with a discrete data set, what would the function look like? So if I start perturbing my classifier here, and I have discrete number of points, right? So for a while, so what am I counting? Probability of making mistakes. Probability of making mistakes in discrete data set is the number of mistakes divided by the total number of points, right? So it's a number of mistakes. How does the number of mistakes change? If I move things slowly, first I make the same mistakes as I've made before, whatever, there are some red points on the wrong side. So that remains the same. And then, boom, I cross over 1 point, I make 1 more mistake. Or the other way around, I make 1 less mistake. So the actual function that I will have would look something like this, right? So this is the real reason we don't optimize 0, 1 loss, is not because it's difficult to do exactly. Well, it's difficult to do because of, the shape, right? So what is the shape? So the function here is now, it's not computed by any program. It is computed maybe by a program, but it's trivial in the sense that you can write down the function that you're computing. It's very simple, right? It's the sum over this whatever. But it is a noisy approximation of the true function that you want to optimize. So there's a true function that you want to optimize, and there is some kind of noisy version of it. And the noisiness is such that the gradient becomes completely useless, right? So this is the problem here. The problem in this particular function is that the gradient is not usable. It's 0 or not defined, right? So let's go back again to these 3 examples. In the first example, we have the situation where the function is computed by some code. It's inexact, and we have no idea how to compute derivative of this function. In this queuing example, we have, again, some sort of simulation process, very complicated. In most cases, not in all cases, but in most cases, it's very hard to compute derivative of that function, you can imagine. And here, we can compute derivative. It's useless, right? It's completely useless. Okay. So what is derivative-free optimization? Okay. So yes, there are 3 terms that are used interchangeably and in some sense wrongfully. I would claim that they're different. They have different meanings to some degree. So we should be careful what we use and it depends on how you interpret. But in literature, often the same classes of methods are described under these 3 terms. So the derivative-free optimization, I would kind of try to define it as class of optimization algorithms that do not use differentiation. As so we all understand what differentiation is. It's from calculus, right? There's numerical differentiation. We will use that, but not actual differentiation. So black box optimization. What is a black box optimization? It is more like a set of applications, not set of methods. Set of applications where the function is black box. So basically, it's like, what should I say here? No derivatives. That's why derivative free. Derivatives by means of, in calculus sense. Okay. Black box. Black box means I have a code. I don't know anything about this code. That's why it's black box. I give x, the code spits out f of x, maybe approximately. That's the black box, okay? That's the. Is it the same as derivative free? I mean, I gave you 3 examples, right? And the third one is not a black box. But you can still approach it with derivative free methods. Okay. Finally, zeroth order optimization. This is the biggest argument of all. I claim that most of the methods that are published under the name zeroth order are not zeroth order. How do you define zeroth order optimization? That is really kind of up to you. So zeroth order can be, so basically it means using zeroth order information, right? What is zeroth order? So uses only function values. Okay, but I would also say does not try to approximate gradients, which really limits the number of the class of methods. This is, not everybody agrees with this, the second one. That's what I think, but okay. Yeah. It's for the online people, yeah. No. So, okay, right. Again, let's look at example number 3. That's why I give this example, because nobody uses really derivative-free optimization for machine learning or binary classification, but you could. Actually, that's not true that nobody uses. People do these days, even for LLM training, supposedly. But maybe for different reasons. But the point is, like, here's an example. In this example, you can use function values only, right? Somehow. I mean, you cannot use gradient. You can approximate gradient. That's a different story. But you may or may not choose to do that. But it's not a black box, right? So these definitions, the first derivative-free optimization is about methods. This is about methods. To me, so this is about application, right? They're not one and the same. It is very often that for these applications, you have to use one of these methods. But it's not necessarily one-to-one. And the distinction I'm making between the first and the third, these methods, is that these do not use derivatives. These also do not use derivatives, but I claim that zeroth order means you don't even try to approximate derivatives, whereas most of derivative-free optimization tries to approximate derivatives. And so the difference is that today I'll talk about this, and then tomorrow I'll talk about that. Okay. Any more questions? Okay. I mean, this is all, you know, kind of rough, whatever. Okay, fine. Applications, loads of applications, really. The more we use computers, right, the more application there are, because the faster you can compute some function, the more you're itching to optimize it. Because if you compute something multiple times, you want to optimize things. So hyperparameter tuning, engineering systems, RL, empirical risk minimization, whatever. I mean, many applications. Complex engineering system covers a huge number of applications I'm not even mentioning. Okay, so now what is the interesting thing about derivative-free optimization versus not, I mean, the derivative-based optimization? Sorry, this is last-minute adjustment. Of course, I made a typo. So the cost of function evaluation is what really we care about. Because usually, as you can see in examples, it is the most cost is in the function evaluation time, because you're running some code. It's not always the case, but it's in most applications that's the case. In most applications, you have some noise. It is very rare that you'll have some kind of application for derivative-free optimization without any noise. And we will be addressing these. These would be the important things that we will be talking about in some sense. The ones that we will not be talking about are these. So I will cross them out, meaning that we will not talk about them. Because there is a lot to talk. I mean, we only have 2 lectures, right? So discrete variables, they often come up, and they're really just no good way to handle discrete variables except for some kind of clever trial and error. There's not much theory. It's very, very difficult. There's a lot of theory to deal with discrete variables and continuous optimization in general, but not in derivative free. Categorical variables, that's even worse. What's a categorical variable? So imagine you're running experiment. Your experiment is a neural network. You're trying to optimize parameters of a neural network. It's a very popular application for black box optimization or for derivative-free optimization. So what are the parameters of a neural network? For example, it could be an activation function. Activation function is not a numerical parameter. It's like you use either LU or something else, right? So it's a categorical variable in principle. So you decide on one or the other. So it's even worse than discrete. It's more complicated. So again, trial and error is pretty much all you can do. Of course, in most cases, you want to do global optimization, but that's a challenge whether it's use derivatives or not. So it's, we're not going to even go there. The other interesting part is, so that usually does not come up. This is hidden and hard constraints is an artifact of the black box optimization, not derivative free. But in black box, you have these hidden or hard constraints. What does it mean? So hard constraint is something that you cannot compute a function, objective function outside of. Because you're running a simulation code, and it may, or some other code that just may not produce a result for certain values of your parameters. It's just not possible. So you have some constraints that cannot be violated. In general optimization, you often can, compute in feasible solutions, and then you kind of like improve the feasibility, blah, blah, blah. You cannot do that with hard constraints, so this is one challenge. It's a challenge, but it's not the biggest challenge. The biggest challenge are these hidden constraints, and they actually happen. It's when the engineers are telling you, okay, well, here is my simulation code that computes a function value for you. Please optimize my function. And then you say, are there any constraints? They say no. And then you give it some set of parameters, variables, and then their simulation code fails because something happens, and they don't know what, because they cannot write down the formula for this constraint, but they basically just tell you, okay, well, too bad, it fails. You have no function value here. So this is a constraint, but you have no idea how to write it down. You can only compute whether it's violated or not by figuring out whether you compute function values or not. Okay, so these are all interesting challenges. As I said, we will not talk about most of them. We will talk about unconstrained case. We will keep in mind that cost of function evaluations is expensive, and then there's noise. Today, we won't even talk about the noise too much, or not at all, but we should still keep it in mind. Okay, any questions so far? Okay, this was introduction. Okay, so now let's think. I start with like the obvious approach. What's the obvious approach? So let's think about it this way. I don't know how many of you have, well, obviously a lot of people here already in a school or in some other ways seen gradient descent, right? Gradient descent, very often when you teach it like you're going down a hill in a fog, you have some kind of a slope that you try to fill and you can try to go down. So what is happening with derivative-free optimization? So you're not on a hill, you're on a lake, okay? And you're trying to find the deepest point in the lake. Okay, so now let's keep that in mind. So what you can do, you can drop anchor and measure the length, right, with some error and with some cost. So what do you do?
Approximation?
Yes. Okay. That's not so obvious. What's the most obvious? I don't know.
Randomly choose a point and
Right.
you know, it's
Assume it's the best point. Like that's it, 1 point. Okay, so what's the
Just look around with your anchor and you like dive it and go where it's the deepest.
right? Yeah. Mm, you're cheating here. Because it means you know where the boundaries are, right? So the lake is actually a very important, let's think of this lake as a finite, indeed, lake. That is, you see, well, you don't see the boundary, but there is a boundary. And that's called level set, right? So bounded level set. So you are, yeah, that's going to be important even today for convergence. But, so that's good. But, yeah.
I mean, you would sample your lake
Yeah.
like with a spread out distribution,
Right.
like Leighton hypercube sampling.
Okay. Wow. Everybody's why don't we just, like, everybody's trying to be so smart. Like, why don't we just do this?
The grid search, yeah.
Yeah, like, right? Okay, so I guess everybody knows that you shouldn't do this. Okay, that's good. We know we shouldn't do this. I'm not going to discuss why, right? It's really bad idea. Okay, but that's the only thing that works if you want global optimization. So, because anything else you're suggesting, obviously, is a good approach, but yeah. But for local optimization, we can do a lot better, and that's what we'll actually be talking about. Okay, so first, I'm going to talk about a method, which is like super curious method. Maybe you have heard about it. It's method from 1965. It is very curious. It is very smart, and it's also very stupid at the same time. It's like really amazing. So this is the 3D representation, but I'll explain it in 2-dimension. It's called Nelder-Mead. It's also sometimes called simplex method because it works with these objects that are simplices, basically. Okay, so here's how this method works in 2D. I actually, sorry, I have this handwritten things written by my postdoc, and I tried to ask ChatGPT to make them nicer, and it was really impossible. It was not understanding what I wanted. It was missing things. So still some places to go. Okay, so I have 3 points that define simplex, right? 1, 2, 3, because I'm in 2D. Otherwise, I'll have n plus 1 points. I have the worst point, the best point, and the second best point. I'm doing something really strange. I'm taking the worst point. I'm taking this face that defines is between the best and the second best, and I'm reflecting the worst point, and that's why it's called R, reflection points. This is the middle point. Through the middle, I do the reflection, okay? So it's kind of natural when you think about it. If everything was like very nicely sort of distributed in terms of function values, this would be the gradient, basically. Okay, so this is my ordering right now, and I'm asking for the function value here, and I can have multiple situations. So the first thing that can happen is that I indeed improved upon my best point. This is like, hey, I had 3 points, now I have a 4th one with a better function value, so I'm really doing better. I'm going to get aggressive, and I'm going to do an expansion. So this is E here. For expansion, I'm just going to double the distance, and I'm going to compute this E, f of E, right? And if I improve the function further, then I'm going to accept this point, and this is going to be my next simplex, these 3 points, which is kind of interesting because I don't know why not these 3 points, because they would be better, but whatever, that method says these 3 points. I'm sure they've tried different things. However, if I don't succeed in improving further my function, that is, it's already great here, but here it's not better, I'm going to go back to this simplex and finish with that. So this would be the end of my iteration. And that happens if this point is an improvement upon the best point. Now, it may not be the case. It may be the case that it's improvement upon the second best point, but not best point. So this is my next option. And so it is better than the second best, but not better than the best. Instead of accepting this, I'm going to do a contraction. So I may have gone a bit too aggressive. I may have been too aggressive. So I'm going to step back and compute this point. It's called contraction, right? So then I will see if the contraction is better than this. I will take this simplex as my next iterate and finish my iteration here. Right, yes. No, sorry. I was wrong. This is a complicated method. So if it was better than the second best, I would just take this and be done. If it was not better than the second best, if in fact it was only better than the worst point, so I went here all the way to the other side, and I improved upon this point, but not either of these points. Sorry, I went here. I'm going to contract and try to be less aggressive, right? And if it works, I'm going to accept this. Otherwise, I'm going to abandon all the pretenses of trying to move to the other side and just going to shrink this simplex around the best point. Why am I doing this? Because basically it says this is my best point. These, maybe I'm looking kind of too far. Maybe I'm making, like very big, wide search. I'm going to look more closely. This looking more closely is going to come up all the time in other methods. Yes?
But if you keep the reflection in that case, you would have at least a little improvement because you're better than the worst point at least. So accepting the reflection would at least improve a little your solution.
So
if you're in the case where the reflection is less good than the second best,
yes.
The worst one, but
Yes.
better than the
Yes, I don't know. That's the way the method works. I believe, right? I mean, I believe I represented it correctly. So if you are worse, if you're better than this, then query this. Yeah. Otherwise, right. If you've done better, I don't know. Maybe it's maybe you can diverge. I mean, we'll see that you may not converge anyway. But maybe it just that definitely diverges in this case. I don't know. It's a good point, but yeah. So in the worst case, if I did not improve at all, I'm not going to go to the other side, but I'm going to, again, attempt two things. The first, rather, attempt one thing and then resort to the other. So the first attempt is to just shrink away, move away from the worst point, but not move to the other side because we're thinking on the other side it's going to be only worse. So we're shrinking this way, and then we're going to compute the function value, and if it improves upon the worst point, then I accept this. Otherwise, I just shrink around the best point again. Okay? This is the way the method is. Now, what is remarkable about this method? There are a couple of things when you think about it. So is it a zeroth order method? Is it a first order method? What is it? Yeah, I mean, presumably it's zeroth order. It's actually more than zeroth. It's less than zeroth order. I don't know. It's -1. So what is most remarkable about this method? This method does not need function values at all. Look at it. What does it do? Okay, so here is the rendition of the method in 2D. This is written exactly what the pictures are. The only thing I'm doing, I'm comparing function values. It works on comparisons. It's amazing. You can do optimization by just comparing function values. And it is actually profoundly important because there are many applications where you can't compute a function value, but you can easily compare, especially when humans are involved, right? You're trying to make them put a value on some, I don't know, consumer basket, right? They cannot do it, but if you give them one or the other choice, they always can choose one, right? So there is, there is really, wonderful, I don't know if people thought about it back when Nelder-Mead proposed these methods, but it's definitely an important feature. Yeah. Okay. Okay. So there is, from now on, anything I'm talking about, there's a chance of stagnation near the local optimum. let's just accept this. That's for sure. The problem with this one, actually, that's why I said it's a stupid method. There is stagnation not anywhere near the local optima as well. So I'll show you that example in a second. There is definitely that I cannot do global optimization. Nobody can do global optimization with derivative-free stuff. There are people who doing very good job in general, but it's in practice, not in theory. Yes.
I also have different divergence, then we should just say this divergence should stop that escapes from a predetermined region. But what if it kind of circulates?
Yeah, it does not diverge. It does not exactly. Okay, so we're ready for the example. Yes. So notice method is done in 1965. The example came in 1996. Maybe nobody cared, I don't know, or maybe it was just not very easy to think about it because the method actually is complicated. And another remarkable thing about this method is that it changes the shape of these simplices, right? And the way it changes the shape of the simplices is actually adapts to the shape of the function. And that is a good thing in general for optimization because that really kind of is almost like a second order method. It really captures the curvature, and that's why the method was so effective. But here's an example, and you can't see the contours. I'm really sorry. Let me try to outline them. The picture here is basically, so the function, and here's the function, and it is continuous, and the gradient is continuous, but it kind of is weird. So here it's very sharply rising on this side, and on this side it's kind of nice and round, and the minimum is here. It's a convex function in 2 dimension, right? So if you cannot converge on a convex function in 2 dimension, what good are you? But it doesn't. I mean, that's the way it is. So this is an example, and basically what happens is that it stagnates by doing these inside contractions because it tries to do a reflection and it cannot do it, and it does this inside contractions until they become flat, and then you basically lose information in the y-axis, and this is where the decrease is supposed to happen, is you're supposed to go south, and you can't because you're just basically not measuring anything there. Okay? Any questions? Yeah.
This method requires you to always find the middle of your points. What if your points are like a trillion of dimensions and finding the middle?
You're out of luck. I'd have to say that in general, in derivative free, which is what we're going to be talking about here, millions of dimensions, you're out of luck. You better choose some subspace which is really important to you and optimize there, and then maybe choose again. Right? It's absolute. I mean, everything is going to be a big issue, and you will see. So we'll now talk about proper methods that actually have convergence and guarantees and blah blah blah, and we'll see where the dimension comes in, and it's going to be an issue. So lots of things can be expensive. Okay. Any other questions about what we did so far? Okay. Take a breath. So we are going to talk today about the basically ultimate zeroth order methods, which are called direct search methods. They came out of basically this idea that the basic one existed before, but the more interesting variety of these methods came out of the the desire to improve upon Nelder-Mead in terms of guarantees, right? So Nelder-Mead, great method, but does not have any guarantees of convergence. So can we do something that has convergence guarantees? Okay. So this is an outline. I'm going to talk about what direct search methods are. They're very intuitive. They're very nice. I mean, so it's much easier to talk about them than any other optimization method almost. And I will introduce it, we'll talk about it, and then slowly we start getting a little more technical as we'll talk about convergence guarantees and convergence rates. Okay. Right. Okay, so the basic direct search method is coordinate search. And this is, in some sense, if we were to talk about what is the obvious approach a little longer, we probably would have come up with it. So what does this do? It takes so these are the definitions, basically. I'll explain to you in a second what does have a picture for it, but the definition is I have a spanning set. I'll define it more rigorously. But this particular spanning set is the set of coordinate directions. Sorry, not coordinate directions, compass directions. So this should be actually called compass search, not even coordinate search. So I can go north, south, east, west. And basically, this is my xk. And for all the directions from this set, so this D is the set of these directions. So D1, D2, D3, D4. And this is the set of these points. And this is called polling set. This is the set where I'm going to compute my function. Okay? All right. So this is how the method works. I start at some point here. I try, say, a point here and check if this function is better or worse. It is worse, right? These are contours of my function, so clearly I'm trying to get here. So this is worse. I try to go here. This is, well, actually, let's not say I try to go here because this would be better, but yeah, it's fine. I can still keep on looking. I can accept it or not. I can go here, and I see that here is a lot better, so I'm going to move here. Maybe I was lucky and chose this one first. I don't know. It really, you can see that there's no good way to know. But once I find something better, I move here. I move here, and now I don't have to go back here, of course. I can measure function here. It's going to be worse. I can measure function here. It's going to be better. I'm going to move here. I can measure function here. It's going to be worse. I can measure function here. It's going to be better. Now I measure function here, here, and here, and none of them are better, right? So at x3, I can measure my function in all four directions, and all is going to be worse. What do? I shrink the steps, right? I just look closer because, you know, it's very intuitive, right? I mean, this is what you would do in a boat. You, like, looks like I'm in some kind of a local basin, but can I find a point that is still lower? So I'm going to look here and here. I'm going to find a better point. I'm going to move here. I'm going to, again, try this. Not better. Try this. Better. Move here, and so on. And then continue this way. Right? Okay. Super easy. Okay. This is coordinate-based search, as described. So start with the pole set. Make some ordering, because I need to evaluate things in order, some order. There's no good way to know which one. Start evaluating F at the pole points following this order. If a pole point is found such that it's better, then stop the polling and move, right? And declare iteration successful. So important concept, successful iteration, we moved. Otherwise, declare iteration unsuccessful after you've tried all the points and you remain in the same place. If iteration is successful, then continue. If iteration is unsuccessful, shrink your step size. Okay, that's exactly what we described, right? Very basic, very simple. Not very efficient. Imagine this kind of method. It's not exactly like, you know, your typical grid search, but it will not be very adaptive, right? It works as it works. It will just keep on going. You may be very lucky that you always quickly find the point of decrease. You can, and then we're going to talk about how you can be smart about different things. But you can try to be smart about which, how to order this. But really, there's no theoretical best way of doing it. Okay, any questions about this? Okay, very simple. An important concept that we need to have is a mesh. Well, we'll have at some point. So what is this mesh? Again, very intuitively, this was my last iteration. This was my step size. So mesh is all the points I can generate starting at x6 without changing the step size. If I just keep on moving, these are all the points that my algorithm can visit. Okay, that's the mesh. It's going to be important. This is the official definition for it, but it's basically, it's like, okay. Now, so I'm going to talk about being a little bit smarter and moving away from just this compass search or standard search direction to something a little bit more general. So for that, the concept that is needed is positive spanning set or positive spanning basis. So this is the first one that we already had. This is the compass. So it's the set of 4 directions, right? 0, 1, 1, 0, 0, minus 1, 0, like this, right? Now, what is this? This is 3 directions, like this, and then another one like this. Now, this is in 2D, right? When you draw something like this, you can eventually, trying to imagine the 3-dimensional, you know, standard vector. No, it's not. This is in 2D. Okay, this is another set which is like this, same thing, but with another point thrown in, which is like that, right? So 4 directions, like this. Okay. So they're positive spanning sets. What does this mean? That means that for any V in Rn, well, these are in R2, but in general in Rn, V is equal to sum of lambda I di, so di in D, lambda non-negative. So it is exactly the same as spanning, except for with positive coefficients, right? So like just in general standard linear spaces, you have bases, you have spanning sets. It's the same thing, but you only can use non-negative coefficients. Okay, and the concept of a basis is the same thing as in regular linear algebra. It's the set that is irreducible. So if you take one element out, it stops being a spanning set. So for example, here, this is a basis, because if you remove even one, you will stop spanning this set positively. This is a basis, and this is not a basis. It's a positive spanning set that is not a basis. Is it clear? Okay, good. So we need that concept. Now, why do we need this concept? Because we're now going to generalize the idea of, you know, just using these kind of directions, and all our directions are going to be coming from some kind of positive sets. And for any positive spanning set or any positive basis, we have this concept of cosine measure, which is very intuitive and very useful for optimization. So what's a cosine measure? So what is this? This is a cosine between vector v and d, cosine of the angle between. So we have some sort of d, right? So d are all the vectors coming from this. So this is our set D. These are the vectors D, little d. Now I'm going to take any vector V. Let me draw it in red. Any vector V. And I'm going to look at all the angles that this vector is making with all my Ds. And I'm going to try to find the one where this thing is maximized. So the maximized cosine means the, you know, most acute angle. So in this case, it will probably be this one, right? So what is the smallest, what's the best aligned vector, right? And now I'm going to go ahead and minimize this thing over all V's. So worst case scenario, worst case V, what is the worst case angle, what's the best angle I can have, right? And it clearly has to be positive. We need it to be positive. Why? Because basically you can think about it. What is V? V will be basically the gradient of the function. We don't know what it is, but it's there somehow. It exists. And what we want for optimization method is that somehow we're taking steps in descent directions. So our D's are the steps that we're taking. We're looking here, there, right? At least one of them should be a descent direction. If we don't have any descent direction, then we're not going to succeed, right? So we need something that is a descent direction. This is where this thing comes from. This basically is telling me, this cosine measure is telling me how much of a descent can I expect with at least one of my directions. And if I look at all of them, I will find the one. That's all there is. It's not, yeah, not that complicated, right? Okay, any questions about this? Now, this cosine measure is an interesting concept. How do you find it? Apparently, it's, in general, it's an NP-hard problem to compute the cosine measure. For, I don't know. At least in some cases, I don't know. I don't work on it, but I was told that it's, or maybe to find the best D's. No, I don't know. Actually, for specific D, you can compute a cosine measure. So this is the very specific, simple case. The coordinate directions or the compass directions, the cosine measure is 1 over square root of n. Okay? So here you go. This is your first glimpse at the fact that high dimensions are hard. So you know that, right? The vectors become more and more orthogonal in high dimensions. So this is exactly where it comes in. So if you have this wonderful coordinate, but compass directions, 2n directions, right? Then the cosine measure is 1 over square root of n. So if n is large, that cosine measure is very small. So you are almost orthogonal to at least some of the vectors. And in fact, most of the vectors in that Rn. So it's that's where the guarantees will start depending on n. And we'll see. Okay? All right. So now we're going to talk about this more general algorithm. And then we're going to prove, well, we're not going to prove anything, but we'll state the theorems and we'll kind of think about them, why they're true. And then we'll look at 2 different types of guarantees, which will make it interesting. So what is the difference between this method and the one I just showed you with the compass direction? There is almost no difference. There is a little bit more generalization, basically. So first of all, there's a search step. It's the step where these algorithms cheat, basically. This is where they turn from impractical methods into practical methods. They are allowed to do whatever they want at whatever cost they choose to find a better point. They can do whatever. They can approximate gradients, Hessians, blah, 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 whatever they want to do, and try different things and be smart. And if they succeed, great. They can do Nelder-Mead. They can do whatever. So why? Because basically, this is just says, if I can improve, I improve. I don't care, right? How? I'll do this for a while. But if I can't improve, this somehow, like I can put anything here without any guarantees. Because if it works, it works. Otherwise, I just move here, right? So this is where the convergence theory sits. This is where the practical aspect sits, basically. So, okay, this is the theory. The theory says, the theoretical part is exactly the same as before, except for it does not constrain me to compass search. It says just pick some spanning set from whatever spanning sets I have. I have like this manual of spanning sets. Pick one somehow. And then, do the thing that I did before. Order the directions in the spanning set, take the step along each direction with a given step size, evaluate the function values in the pole set. So the pole set is where I need to look at the function values. If I found a point where something is smaller, then I'll accept this point. Otherwise, and the iteration is successful, otherwise it's not successful. If it's successful, then I either keep the same step size or I can get more aggressive. That's fine too. I can increase the step size. The important thing is that if I did not succeed, I have to decrease my step size. That's very important. And it is betas and gammas are just making things complicated, but it's just for flexibility. Okay? Right. So once again, I just want you to notice that so far, we are only working with function value, the function comparisons, right? Only function comparisons. Okay, this is going to change, unfortunately, as soon as we want anything theoretically sound. But the algorithm does not need anything but function comparison as it is. Okay? Right, good. So convergence. So now we're going to talk about convergence. So the first assumption that we always have to make, otherwise it doesn't make any sense, is that the function is bounded from below. Duh, okay. The second is less obvious, but often made assumption is that its level sets are bounded. This is about lake being enclosed, you know, in the shores. So you cannot sail off to whatever, right? To the Americas. Assumption number 2, if there exists an alpha such that so basically a lower bound, so if your step size remains bounded away from 0, then the algorithm visits only finite number of points. Okay, this is the assumption. And the theorem says, under this assumption, the step size will have to go to 0. I mean, this is, how do you say, proof by assumption. It's not quite proof by intimidation, but it's also as bad, right? What is this? It says, if the algorithm behaves in a certain way, then it behaves in a certain way, basically. So if it only visits finite number of points for any positive alpha, then alpha has to go to 0. Well, duh. I mean, like, why are we doing this? Like, why are we talking about this? Amazingly, this is just for convenience. Obviously, we're going to try to show that this assumption 2 holds under some other much more natural assumptions on the algorithm. And then we'll also show that this theorem 1 is just a kind of a step towards proof of actual convergence that we want. So first, we're going to basically say that, well, this theorem 1 really means something as soon as we put conditions. No, that's exactly the point. It doesn't converge to A. It has to converge to 0. This assumption 2 says that if it is bounded away from 0, that means the algorithm only visits finite number of iterations. The way the algorithm works, it will never stop. There's no stopping the algorithm. There's no stopping criteria. There's nothing. So it will continue working. So if it happens to visit only finite number of iterations for any alpha bounded away from 0, that alpha has to go to 0 because it's an infinite algorithm. No, if there exists, an alpha such that it means it, only visits not finite number of iterations. Yes. Yeah. Right. Exactly. Yes. Right. Yeah. It cannot exist. Basically, that's what it is. Yeah.
Just for assumption 1, if you just consider that the set is a cone, can you just take the closure and the proof the set? Because in the case of black box, if it's really discontinuous, it's really hard to find that it's close.
Oh, level set. Yeah, I see what you're saying. Yeah, I think. No, right. So you'll see. This is the next slide, actually. So here's what we're gonna do, right? So we're gonna make. Okay. So it depends what you do. So okay, under these nice assumptions, we'll talk about in a second. We're gonna have the limit result, meaning that the algorithm actually converges to somewhere where the gradient is 0. but also this, right? So, okay, I don't exactly remember all the steps here, but my guess is that this would definitely not be possible to say, because this says that there's a limit point such that the gradient is 0, and if you're not in a compact set, even if you're a bounded set, the closure, yes, so X star may belong to the closure, but it will not be necessarily in whatever that, yeah, I don't know. So whatever that X star is. So that's where you need that. So if you can just, if you're happy with the closure of the level set, then this is fine. You can just make that assumption. This comes from essentially this fact and the continuity, Lipschitz continuity of the gradient. So Lipschitz continuity of the gradient, this is important actually. I'll probably review it tomorrow, but I mean, you guys, some of you had seen gradient descent, obviously, like Lipschitz smoothness, is that something very, okay, yeah, but not everybody here was for topic A, but I assume if you came here and you were not in topic A, you should at least know what gradient descent is. Yeah, advanced optimization, right, that's okay, got it, yes, okay, great, I may skip it tomorrow then, doesn't matter. So this is it's not, I mean, this is not a standard assumption. There's a lot of non-smooth optimization algorithm, but you know, the stuff I'll be talking about is for smooth. So things are a little bit different for non-smooth. So we're assuming that the function, that the gradient is Lipschitz smooth, Lipschitz continuous, and then, okay, here's the important part. The important part is basically that whatever direction set of directions we pick, the cosine measure is bounded away from 0. So we cannot get really bad angles with the gradient, right? We always have some kind of a, you know, at least some positive angle, right? Some positive cosine. So that's thing number one. And then the directions are bounded. That's just, yeah, otherwise it's difficult to do anything if we allow random unbounded directions, right? And even if alpha goes to 0, then your steps are still not small, so it's kind of crazy, so you don't want to do that. I would always think that directions can be scaled so that their length is at most 1, but you know. Okay, so this is important, and this is where this thing comes from this theorem 1. So theorem 1 says step size goes to 0, and essentially from here, it says that if under this condition step size goes to 0, it means gradient goes to 0. And we'll see how it actually kind of results in some things. But okay, so this is important. We're still making this assumption too, right? Which is bogus assumption. So now we're going to talk about how we get this assumption too in 2 different ways. Yeah.
You said earlier in the beginning of the presentation that the functions were noisy. Is there a way to weaken these assumptions? Assumption tree, precisely.
Right. Yeah, yes. Okay. Right. So I can talk a lot about, I'll talk a lot about it tomorrow because I have like all the kind of formulas for these things tomorrow. But it's, definitely. So I'm actually, I'm pretty sure there's a lot of theory for noisy direct search. There's also theory for stochastic direct search. So there's definitely various ways, but we haven't even gotten to, right? So, okay. One of the interesting parts is that I keep on talking about how we work with function comparisons. I'm going to move away from this in a second because actually all the theory, more or less, for direct search, except for what's on this slide, is based on function values. So once you have function values and you have errors, then it's one thing. Once you have function comparisons with errors, that's a whole other interesting thing. And there's very little work on that. There's a little bit of work. I think Ben Recht and Rob Nowak did something, but they, like, it was a while ago, and I've seen some work, but I think it's not super advanced. So when you think about it, these function comparisons can have errors, right? But the errors would be like a 0-1, like wrong direction. But then you have to, if it's a deterministic thing, then you cannot prove anything. If it's a stochastic thing and a probability, then you have to define probability depending on what it, like, we can talk about it at other times. It's interesting. It's interesting stuff. It's definitely very interesting stuff. I'm talking about the basics. So, okay. So what am I trying to say here? This is basically, this is where the mesh comes in. So there's two assumptions here, which are really technical, and they're talking about basically what kind of basis I'm picking from, what kind of spanning set I'm picking from, and what kind of adjustments I do to the alpha step size. But these two things together, don't read details into them. What they're telling me is that for any fixed alpha or any bounded away from zero, I'm going to generate, this algorithm is going to generate a finite mesh. So remember the mesh? So this is basically the very geometric condition on how this mesh is generated. And if I'm generating a finite mesh, well, it's not a finite mesh, it's an infinite mesh, but if it's in a compact set, it's a finite mesh, which basically tells me that I will have this assumption too. So if I don't shrink alpha to zero, I will have to I can only visit finite number of points. And I cannot cycle, right? I cannot go through the same point twice because I always decrease my function value. So I cannot possibly visit the same point twice. So if I have a finite number of points to visit, that's it. That means I have to shrink alpha, and that means I will converge, okay? Yeah, right. So in some sense, any optimization algorithm probably can be viewed as exploration without exploitation. Exploitation without exploration. There are some methods that also would, and tomorrow, well, I'll kind of talk about things that you can think of doing. Well, okay, you can have some exploration too, but yeah, you can definitely think of it as just exploitation. Yes, I mean it's, but there's no randomness. There's like it's just much more sort of narrow. Oh, I see. Okay, sorry. Yes, okay, yes. I mean, yeah, I guess. I mean, yes, it's a search, right? I don't know. Yeah.
To kind of answer that, I think our goal is to find a local minimum, not a global.
Yeah, that's right. Exactly.
That's why we
Yes.
don't do exploration.
Well, I mean, it is still exploration to some degree, but it's not like our goal. This is all we can guarantee. Our goal is, of course, find the global optimum. And in some sense, that's why we would want to start maybe with large step sizes, because it may help, right? But yeah, I mean, guarantees are not there. And the only way you can guarantee with exploitation, global optimum is you're going to run things forever, and it will never stop. So therefore, you will find a global optimum at infinity. Right? I mean, you can always do that. It's fine, but yeah. What? Sorry. I don't know what direct reference optimization is. I'm sorry. I mean, these methods are not used in, as far as I know, that much in a setting of just function comparisons. I just want you to, think properly in terms of what information is being used by an algorithm and what guarantees we have, right? This is important because it wasn't really, when papers about these are published, it's not emphasized that it's function comparisons only. But this is where it ends. This is the point. This is convergence guarantee for the algorithm on comparisons only. The very next thing I'm going to do is demand that we have function values. Okay, and how am I going to do that? Is by saying that I will no longer accept a simple decrease. I will no longer accept steps where one function is smaller than the other. I will have to have sufficient decrease. So now there's a value involved, and this value means that I have to have these values, at least approximately, at least somehow, right? I have to have these values because I insist that the decrease is proportional to alpha k to the power of p. And this p is 2, really. I mean, theories for any p, there's no reason to have p anything but 2. You will see that in a second in the results. Okay, so it turns out that if you have this property, then you can have the same theory, but without the mesh, right? You don't need the mesh. That is by itself, that's not an achievement. The achievement will be in the convergence rates, but this is an alternative. So instead of sticking to the mesh, you can do whatever you want as long as you only accept the sufficient decrease. The sufficient decrease is nothing new. gradient descent, Armijo condition, many other algorithms, like in optimization, you need some kind of sufficient decrease to guarantee convergence. So this is basically where it comes from, okay? But this is the key thing. It no longer accepts function comparisons. You have to have function values. Right, and this immediately gives us much more than convergence. It gives us complexity. Okay, so I'll just explain what complexity is, although probably everybody already knows, but what do we want from complexity? So complexity means that, let's say, T epsilon is equal to the minimum iteration case such that gradient of f of xk is bounded, is smaller than epsilon, right? So this is the first time my gradient goes below epsilon. It's the first iteration when my gradient goes below epsilon. In convex optimization, it can be when the function value is closer to epsilon. So what I want is T epsilon is less or equal than some kind of function of epsilon, right? This is what I want. This is complexity bound. So for gradient descent, for example, the complexity T epsilon is order of 1 over epsilon squared. Well, L, in fact, right? Something like that. For DFO, for derivative-free optimization, T of epsilon is expressed as two functions that depend on epsilon and on the dimension. Complexity for gradient descent is iteration complex. Number of iterations does not depend on the number of calls to gradient, does not depend on the dimension. But in DFO, it is always depends on the dimension. So we're going to look at something like this. Okay? That's the complexity. Complexity in DFO is an interesting topic, not very well discovered yet. Okay, this is complexity consideration, DFO, same thing. Okay, so I know we're running out of time, but we're kind of almost done here. So here is the result. It looks messy, but what is this key result? This key result says that because of all these, sufficient decrease condition, I will not be able to make a successful step, or actually the other way around. Sorry. Well, okay. If my step is unsuccessful, it means my step is too large. Basically, that's what it means. Okay, so I can say unsuccessful implies alpha k too large. Right? This is this complicated formula. You can see what's involved. Cosine measure, maximum direction length, alpha k, cosine measure, minimum direction length, alpha k. So alpha k here, together, p is bigger than 1, right? So together, this thing is bigger than the gradient. So alpha k has to be too large somehow. Then you have this complicated theorem, which counts the number of successful iterations you can possibly have. Because, and don't worry about looking at the details, but this theorem says that if alpha if iteration is unsuccessful, alpha is too large, which means that as soon as alpha is small enough, iteration will be successful. But what is small enough? This is bounded away from bounded below by epsilon, right? We're counting number of iterations until gradient goes to epsilon. So until then, gradient is large. It's bigger than epsilon. Okay, so if gradient is bigger than epsilon, so is alpha is bigger than epsilon. So as soon as alpha is smaller than something related to epsilon, we should have a successful iteration. And on successful iterations, we get a decrease proportional to alpha to the p, which means that we decrease our function by a fixed amount. We cannot do this infinitely many times. This is what this counts. This counts how many times we can decrease the function value. There's this where we start, the lower bound, blah, 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 the decrease on every iteration, all complicated things. In the end, we get this result, final complexity T of epsilon is bounded by this. And there are two terms here. The one depends on n, the one depends on epsilon. So if P is 2, which you can kind of easily see that P equal to 2 is the best choice. But if P is 2, then this P is 2, this is 1, so this is e to the minus 2. And this is square root of n to the 2. And there's n here, so there's n squared to epsilon minus 2. Okay? And then there are all kinds of constants, depending on your cosine measure and the Lipschitz constant of the gradient and the way you adjust alpha and blah, 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 whatever, all that stuff comes in. But this is the key complexity. Okay? So, what is the point? If we have the sufficient decrease condition, we have finite time guarantees for this method. With the mesh, basically, argument, which is when we did only comparisons, with the mesh argument, we can visit every point in the mesh. At least so far, there is no better argument. If you visit every point in the mesh, complexity is exponential in n, right? Because mesh is, number of points in the mesh is exponentially. It's like, basically, it's like the obvious approach that we discarded to begin with, just visiting every point. So, not good, but that's the way we are. Next time I'm going to talk about, tomorrow I'm going to talk about approximating gradients and the convergence guarantees and complexity guarantees with that, which is interesting. And we will try to understand whether this is the best we can do. The answer, I don't know, which is kind of strange. There is a yes and no answer to some degree, and I'll talk about this tomorrow. So basically, yes, we will, next lecture, using function values to estimate gradients. Thank you.
We have some time for questions, unless everyone's tired.
Yeah, okay, so you mentioned the complexity for this condition.
Okay, so you mentioned some complexity with that condition, but there was no complex method, and this method is the grid. Practically, can it behave better than one direct?
Sorry, these are all direct search, right? In some sense, it's a big class of methods. But you're talking about the one with mesh versus the one that function comparison. I think the practical aspects. So, as I said, to me, the biggest difference is whether you do comparisons versus actual function values. But if you're computing function values already, if you actually have function values. In practice, there is not a lot you gain by imposing this sufficient decrease. In fact, so tomorrow I'll talk about model-based methods. I'll mention a little bit Michael Powell, who pioneered a whole bunch of them. And he has some incredible software that works really well. And he basically said, despite the theory, just, your function values are so expensive. If you get something better, take it, right? So in practice, you would do that. This sufficient decrease condition is mostly theoretical. In fact, when we have noise, we even relax it a little because, then we may want to allow it to be not even a decrease, but slight increase. Yeah. I don't know if it answers the question. Yeah. Yes, exactly.
But you mentioned when you have noise, you relax it. But from my experience, you don't relax it in their beta, or is it just?
No, you should. You actually should. But it depends on. It depends again. People often don't relax it, but it depends on the noise. It depends on in various situations, really. Yeah. But for proper theory of line search with noise, you should relax the condition. Yeah.
question about the clarification on the bound of the complexity about the stuff inside, because there were a ratio between a function h1 and another one h2, taking argument x respectively x and Betson. I just wondered, do you have any conditions that have to be validated for those functions for this result?
Yeah. So it's basically you're asking about lower bounds. Yeah. I've skipped that. I think that's what you're probably saying. So, like, you know, we're expecting to bound the complexity in terms of number of, in terms of epsilon and in terms of dimension. I mean, I do believe dimension is essential. I don't think we can not depend on dimension because it's, you know, but again, there is no, I mean, this function h can be 1, right? It does not have to depend on dimension in principle. So the question is, are there lower bounds? Can we say that it has to be at least order of n or something? I don't think we know that. It is very interesting because, so I haven't seen any lower bounds. I've seen lower bounds for stochastic DFO, but they are very heavily dependent on the fact that functions are really badly behaved stochastic functions. On deterministic DFO, I haven't seen anything. And the lower bounds that exist in the literature, I'm actually kind of trying to look at them now, but the lower bound, for example, the classical lower bounds for gradient and first order methods come from Nesterov. And those lower bounds only apply once your dimension exceeds basically the number of iterations. So it's, it really is, like it's dimension independent, but dimensions are chosen to be specifically large. So once you restrict the dimension, these lower bounds no longer apply. I don't know how to work it, but maybe somebody will figure it out soon. I don't know.
Maybe one more question.
It seemed like we were not assuming that all of the vectors in this positive spanning set we chose are the same in length. Is there a reason for that? Can we find improved performance by not requiring that?
It's a good question. I mean, I don't exactly know. So the interesting part is that there is extension of this work, which also I didn't have time to talk about randomized direct search. So if you produce random directions, for example, Gaussian, you can actually show that you have this finite positive cosine measure with high probability. And then you have also a very good successful rate, but you don't need as many directions anymore. You can just compute 2 random directions and you still have a positive cosine measure with high probability, which is quite incredible. So it all of a sudden doesn't depend on the dimension. Now, the number of iterations will depend on the dimension more. So there's no free lunch, but there is, yeah, so at least in that, I would say it is definitely useful to have not fixed direction. Otherwise, I mean, yes, think of Nelder-Mead, right? It kind of stretches out. So if you know something about your Lipschitz constants in different directions, for example, right? I mean, you could even adjust your alphas differently in different directions depending on your past success. You can be smart about it, and then you can think about it as same alpha for theory, but different lengths. Yeah, so you probably can do it. Okay, right. So, okay. Right. So this is it's an excellent question. It's a very big philosophical question, right? So basically, what I showed today is one of the very basic ways to do complexity analysis. You get the same thing in you know, in line search or in just general gradient descent, which I'll talk a little bit tomorrow, or in trust region that I'll talk about as well. Anyway, so all of this is deterministic. Now, what the person is asking about is a stochastic version of it. And the stochastic version of it came out exactly the same way. It just basically take deterministic analysis, assume that all these properties hold with high probability instead of always, and see if you can actually still show convergence. So we, indeed, with stochastic stuff, we just followed the deterministic stuff and put it into a stochastic process. So we borrowed everything from deterministic and then, you know, put it. So yeah, lots of these things extend to stochastic setting, but in a, as Courtney knows well, in sometimes with a really, really great pains.